3 plus c. So we theoretically can handle any quadratic that's missing an x term. Okay? All right. Deep breath. How about a constant over an irreducible quadratic? So what do I mean by irreducible? I can't factor that over any of the rational numbers. So like if I put up a quadratic here, that's factorable, right? You can factor this x minus 4 times x plus 1, right? This one does not factor, and you need to know that just by looking at it, kind of doing a quick little mental inspection. You're not going to be able to come up with the numbers that are going to work here, right? All right, so that's what I mean by irreducible. In the event that you have an irreducible quadratic on the bottom and a constant on the top, here's what you do. You complete the square of the denominator. All right, we're going to complete the square. So let's just do that. That's its own work. Complete the square. All right. You write down x squared plus 2x plus 17. Now we're about to find out whether or not you'll know how to complete the square. All right. So can anyone help me out? Like, what's the procedure for completing the square on a quadratic? It's been a while. Yeah, you're starting, like, the neurons are firing there, somewhere in there, right? Lost in the cracks of your short-term memory. Okay, so let's see if this rings a bell first. You must have a 1 in front of the x squared to even begin. All right? You cannot begin completing the square until you have a coefficient of 1 in front of x squared, which we do. All right? On the next example, we'll do something that doesn't, okay? Now, after you've done that, make sure you have that 1. Anyone remember the next step? Okay, good. You take the coefficient of the second term, and by the way, this needs to be in descending order. Okay, so just make sure it's x squared, then the x term, then the constant. So you're going to look at the coefficient of the x term. You're going to take that number, and what are you going to do with it? So it's positive 2, right? What do you do with that number? Divide it by 2, and you always divide it by 2. So if that would have been a 4, you would divide it by 2. 4 divided by 2. If that was a 5, you go 5 divided by 2. Right? And 2 divided by 2 is 1. I'm going to box that number. It's going to be an important number for us. I'm going to use it later. Do you remember the next step? Square that number. So take this number, 1, and square it, and we happen to get 1 again, right? And that's the second important number. So we're always going to get 2 numbers when we complete the square. I call this the first magic number and the second magic number, even though they're not magic. Okay? Anyone remember the next step? You add it to the other side. You have to add. So which number are you saying I need to add? This one or this one? The one? This one, which is the one that I need to add? It's the second one. Okay, so now what we're going to do is we're going to take a look at this one right here. And I'm being told I need to add it to the other side. I need to add it to both sides. Does that sound familiar? What's wrong with that, though? When you're saying add it to both sides of what? There's no other side, right? But there is no other side. That's what I'm saying. Why? So this is why this is an important concept, because a lot of you are taught in college algebra, and I'm not saying that you were taught incorrectly, but what you were doing in college algebra is you were trying to solve this equation. And so what they taught you to do was complete the square, which is everything I'm doing here. You would get that 1 and you would add it to both sides of the equation. But that's because your goal was to solve an equation. Here our goal is not to solve an equation. But can we still complete the square? The answer is yes, but since we don't have an equation, we are not going to create one. That would be very bad. We do something different. Here's what we do. We write x squared plus 2x, and then right here, we're going to add nothing. And then we're going to say plus 17. That's the same expression, isn't it? So as long as I don't add anything here, I'm dealing with the same animal, right? Now the way I'm going to choose that nothing is going to be clever now. Instead of writing 0, I'm going to use this number. And I'm going to add it and subtract it at the same time. And when I add and subtract it, that's still a 0, right? And then I still have the plus 17 here. So everyone agrees that I have not changed the problem, I just changed the way it looks. Yes? When you do this, if you did this properly and you took it and divided by 2 and you squared it, and you took that number and you added and subtracted it, if you did that all correctly, you are guaranteed that the first 3 terms are a perfect square trinomial, meaning that does factor, guaranteed. It factors to be actually the same thing times itself. The question is, what is it? X plus 1 squared. Now, how do I know it's x plus 1? Well, I could just know that when you factor that, you get that. But if you really want to know, like if you're lost this number right here, guess where that comes from? That's that first number. So see how that's a plus 1, a positive 1? That goes here. With me? We're going to do another one of these, so we'll have an opportunity to refine things here. What's still left out here, though? These two, right? What's that? Plus 16. So if I were to take x plus 1 times x plus 1 and I FOIL it all out and expand, I would get back this, and then if I put those two together, I'd get back this, and I'd be back here. So that is just another way of writing this, isn't it? Just another way. It's the same exact problem. But let's see what it gains us. By doing this, let's see what we gain. We're done completing the square. Let's rewrite the integral. The new integral is 1 over that. X plus 1, that quantity squared plus 16 dx. Now squint your eyes, and what does that look like, kind of? 1 over u squared plus a squared, doesn't it? 1 over u squared. 1 over u squared plus a squared. What's u here? X plus 1. So if I were to make a substitution right now of u is equal to x plus 1, what would du be? dx. And that's good because that means I'm not going to need to scale by anything, right? And this formula, this integral should just turn right into integral 1 over u squared plus 16 du. And that I can use my arctan formula for. The arctan formula is 1 over a, so 1 over, what's a? 4. Arctangent of u over 4 plus c. And the final step would be to replace u with x plus 1. The question is, do you have to do this u substitution? Could you just go straight from here to here? I would prefer you just go straight from here to here. But again, you know, people are at different comfort levels right now with this. So I'm trying to show you, look, to get from here to here, there's the formal way of doing it. But you should be able to recognize, given enough practice, that this is going to go straight to that. Questions? Let's recap. Constant over linear, we're good. Constant over repeated linear, we're good. Constant over quadratic with no x term, we're good. constant over irreducible quadratic, we're good, right? If somebody gives me an irreducible quadratic, I should be able to complete its square, and I should be able to do this, right? Theoretically. I'm going to give you another one before we move on to example 7. I want to do, let me get it ready here. Let me change this problem real quick. Okay, what about that? That's a constant over an irreducible quadratic. Now, I changed the problem, so this is a constant over irreducible, not linear. So the technique for this is to try and complete the square of the denominator first. So I'm going to complete the square. I write down 4x squared minus 4x plus 3. Yeah, and you can't have a 4 in front of the x squared. So you have to factor it out. The problem is that you can't really, it doesn't look like 4 is a common factor for all 3 terms, but we can still force a 4 to come out. Here's the 4. We have x squared minus x, and then this last term is going to become what? 3/4. If you distribute that 4 back through, everything's correct, yes? All right, now, just focusing our attention inside the parentheses, I need to go ahead and run the completing of the square. So I've got a -1 here, right? That's a -1. I'm going to take that and do half of it, right? So I'm going to take -1 and take half. And that's just what? -1/2? That's my first magic number. And then I take that and square it. So if I take -1/2, square it, I get 1/4. That's my second magic number. Bless you. Now I will rewrite this expression. I will bring the 4 with me there. X squared minus x, and then here's where I have the hidden 0 right here, plus 0, and then plus 3/4. What am I going to replace that red 0 with? Plus 1/4 minus 1/4, and it must be in that order. You don't do minus 1/4 plus 1/4. It's got to be the positive one first. So rewrite this. 4x squared minus x plus 1/4 minus 1/4, and then plus 3/4. Still good? This is 4. All right. These first 3 terms, you know what, let me erase that last piece. These first 3 terms are guaranteed to factor to be a perfect square trinomial. Yes, this is a perfect square trinomial, so this will factor to be something times itself. That something will be x and then minus 1/2. And if you don't know where that came from, it's this number right here. So x always goes here, then minus the 1/2. And you could check that, right? You could FOIL that out. Do we need to check? No? You believe it? If you FOIL that, multiply it times itself, you'll get this. And then you have to put these 2 together. They have the same denominator, good for us. And that's going to be plus 2/4, which is 1/2. Still good? All right, let's rewrite the integral. What about this 4 out here? Should I try and distribute that back through? No, I'm going to take it out of the integral completely. So it's time to rewrite this. This integral now becomes 1 over 4 parentheses, parentheses, x minus 1/2 squared plus 1/2, close parentheses, dx, which is 1/4 integral 1 over x minus 1/2 quantity squared plus 1/2 dx. And the whole reason we did that was because that's going to look like what?
17.
That looks like formula 17. Just be careful on these. When you do this process of completing the square, sometimes this will turn out to be like minus a half. And then the formula is not 17. It's 20 instead. So just pay attention to this. If these two numbers right here come together to become a negative, then you wouldn't use formula 17. Make sense? But in this case, we have formula 17 again. Do you all want me to make the U substitution, or you just want to write the answer down? Skip the U? Skip the U sub? Please don't speak over each other like that, okay? Give everyone an opportunity to... 1/4 is out here, times. Oh, wow, we never talked about what A was. Ooh. That right there is A squared, right? So if A squared is 1/2, then A is root 1/2, which is the same as 1 over root 2, because when you have a fraction, you can do root top and bottom, right? So A is 1 over root 2. Yeah? Okay. So let's go to the formula. 1/4, and then it's times 1 over A, but A is 1 over root 2. Do y'all see that? 1 over A. Arctangent of x minus a half. That's kind of like the U, right? U over A again. 1 over root 2 plus C.
Whenever we're doing these or writing them like for a test or something, do you want us to do like show you like the zero part, or can we just automatically do like minus?
Show me the zero part.
Yeah, because like when you write it, you write.
Oh, when I did like plus 0? You don't have to show that. Mm-mm. Now, but do show me like plus 1/4, minus 1/4.
Yeah.
Like make sure you include that.
Just go straight to
Yeah. Mm-hmm. All right. I could clean up a little bit because 1 over a fraction, this flips, right? So that's really, this is really just what? Root 2? Okay, so I could put that together with the 1/4. So I could have something like root 2 over 4, and then arctan of x minus a half over 1 over root 2, and then plus c. In the back of the book, they would probably flip this one up too, also. And if I flip that up, it's a root 2 that would pass through the top. But I'm just going to leave it like that. On the test, I would give you full credit for that. Now, in my 9 o'clock class this morning, we were talking about this. And we were talking about whether or not it's acceptable to leave an answer like that. So let's take a vote. How many of you were told to never leave a root in the bottom like that? Yeah? How many of you were told it doesn't matter? Who told you that? Oh, I told you that. Okay. And I told you why, right? Do you remember at all? No? Did I tell you why? I'm going to tell everyone why. Okay, so look, because this bothered me as a student, I was told the same thing you were told. Do not leave roots in the bottom like this. Bad. It's wrong. Some people will count it wrong if you leave it like that. So it really bothered me. So as I became more mathematically informed, I was able to get down to the reason. All right? So here's the reason why you were told not to leave it like this. It's because the person who told you that was told by someone also to not leave it like that, but really never given a good reason why. So if we were presented with this, what would you have to do according to someone that told you you can't leave it like that? What would you have to do to that? Multiply by root 2 over 2. This is called rationalizing the denominator. So then you multiply straight across, you get root 2 over 2, right?